So basically hearing, let's move on to this. This is one of the second biggest kind of senses that we're going to talk about. And it basically follows the same signal, same direction. First you get detection, then you get transduction, and then it gets transmitted to your brain, and then that becomes stimulation. The sense of hearing is also called the sense of audition, like oral hearing. And let's talk first about the sound waves. Again, much like light waves and color, the things that define sound waves are frequency, how high, how shrill, or how bassy it sounds, or how loud, that's basically frequency, and pitch, right? So when we listen to, say, an orchestra, which I love to do, we could even hear it all. It's amazing that our ears are so sensitive and tuned that they can hear all the bass notes, the drums and percussions, the winds and horns, all at the same time, creating like this really nice musical tapestry. How is it that the ears can separate these different timbres and sounds? It's pretty amazing. Before we talk about that, let me make sure to understand that the term decibel, it measures the loudness, the volume and intensity of sound waves. Okay, let's see how an outer ear is how an ear is organized. Okay, so what is this? Okay, so basically this is what happens in the ear setup. Out here in the outer ear, there's basically only a couple of things. This is your ear, your outer ear, also called the pinnae. And so that acts as a kind of a cup to pick up sound waves that come in. Mine sticks out a little bit, so maybe I can hear better, I don't know. So the sound gets transducted, gets moved onto the ear canal, right? Basically we all know what the ear canal is. That's where our wax is, that's where we use Q-tips to clean out. And then it hits the tympanic membrane, also known as the eardrums. Basically this is kind of a thin membrane that vibrates, it hears noise, and it goes back and forth like that. And connected to the eardrum, or the tympanic membrane, is the other name for it, are three bones: the hammer, the anvil, and the stirrup. These are the three smallest bones in your body, and they're kind of interconnected. And they are interconnected to transmit vibrations again. So as the eardrum vibrates, it vibrates the hammer, which does the anvil and the stirrup, and then it hits what we call the oval window. The oval window acts like another tympanic membrane. And basically, the oval window is connects to the cochlea. Basically, the cochlea is like a horn-like device. It's kind of like a tube that's filled with liquids. And so when the oval window vibrates, the liquid in there vibrates too. And within each of these liquids in the cochlea are cell hairs. They're like little hairs, and that can pick up the vibrations in the cochlea. So that's how you hear things, is that the vibrations, the air vibrations, conducts here, turns into kind of liquid vibration that moves your hair cells, and your hair cells transmits that information into neural signals that transmit to the brain. And of course, let's see, here's some pictures that I put up. This is exactly what the cell hairs look like inside the cochlea when they're actually enlarged. They're not this size, of course, it's much, much, much smaller. Right? And so they respond to the vibrations in liquid by transmitting into neural information into your brain. And where in the brain does it go? It goes into the temporal lobe here, into the auditory cortex. Now, just like how in color we looked at two different theories that understand how our eyes perceive color, there's also some theories that talk about how it is that our ears can hear different pitches. So you can imagine that the loudness makes sense, right? The louder it is, the more your tympanic membrane vibrates. And the more it vibrates, the more your cell hair moves, and that's how your brain picks up how loud something is. It's not clear, however, how it picks up pitch. And there's kind of two theories. These aren't competing theories, these are all complementary theories that describe how our hearing works in terms of pitch. The first one is place theory. This is devised by German researcher Hermann von Helmholtz. Basically, in place theory, they say that in your cochlea, let me draw you what it looks like. It's kind of like that. It's like a large kind of tube. In the cochlea, there's different kind of cell hair places, and in different places, they pick up different signals. So for example, this here picks up, say, high-pitched signals. This one is medium. So on and so forth. So basically it's like, imagine you have a giant sheet, and if you shake the sheet, like if you poke at one place, only that place moves. That's the place that picks up that kind of vibration. Here is another sound of vibration. However, there is a problem because it seems like the cell hairs doesn't respond to really low frequencies, what we call the bass. So they have to come up with a different kind of way to understand how is it that your ear picks up these low frequencies. And so they come up with the frequency theory, which is the idea that not only does the hair move, the entire cochlea also vibrates and picks up that signal. So if you're hearing something really low, like 10 vibrations a second, your inner ear also vibrates at 10 vibrations per second, and that transmits that information to the brain. So the brain is able to convert that vibration information into neural impulses, into understanding. It's like, oh, this is the sound of a double bass, or this is the sound of an electric bass. So these two theories work together in explaining how is it different pitches are picked up in the ear. High pitches are done with place theory. Different cell hairs pick that up. Frequency theory says that your ear picks up the lower vibrations and sends those vibration information to the brain, and then your brain can combine them and have like a beautiful orchestral kind of patchwork of what it sounds like. Still pretty amazing to think about. Moving on. Another thing about hearing is that how we locate the position of the sound. Not only do we hear it, our brain is actually kind of made to locate where the sound is. You might think, well, why is it that we have ears on both sides of our head and not just like a giant ear hole right here in the middle of our face? And one thing that helps us survive in the terms of evolutionary psychology might be that knowing where sounds come from was an advantage. And so there's really two things that help us locate a sound. Let me just draw a person. And here's the ears, right? That's their ears. This is from the top on, so their eyes are right here. And that's their nose. Eyebrows. Oh, look, he's happy. And so imagine there's the sound coming here from, say, their really high-end stereo system. So two things are different, first of all. Number one, this ear, the one closer to the location of the source of the music or noise, has a higher intensity. It's louder on this side, right? Because on the other side, your head actually blocks some of the intensity. And secondly, what's different is that this ear gets that information first. Now we know sound travels really fast, and so the timing difference between this ear and that ear is very small, infinitely small, down to the like 2 to 3 decimal points of the millisecond. And however, our brain is so fine-tuned that it could even tell, based on that short timing, where that information of sound is coming from. And so those are two information we use to locate sound. The differences between the left ear and the right ear in terms of how intense the sound is, and also the timing. So it's pretty impressive that our brain can do all this. Okay, any questions on sound? So let's look at where in the brain, again, that auditory information is processed, and incidentally it's named the auditory cortex, and it's right here in the temporal lobes over here by your ear. And again, just like in vision, where we have multiple processes going on being decoded at the same time, what we call parallel processing, our auditory cortex has that too. So it looks at things like timbre, intensity, sound, pitch, echo, flow. So if you listen to a musical piece, there's so many things to keep track of, right? There's the drums, the percussion, the lead guitar, rhythm guitar, there's a singer. And so there's like 100 different things going on, and yet our hearing, or this part of the brain has evolved that could parallel process all this information at the same time. Really impressive. Gives us a really beautiful way to understand our world. Okay, let's look at deafness now. What happens when people go deaf? Now there's two reasons biologically that people can go deaf. The first one is called conduction hearing loss. So in the conduction hearing loss, there's something that goes wrong with the tympanic membrane or the bone, or the three bones in the inner ear. That for some reason their conduction goes bad, and they can no longer transmit the vibrations of the sound properly to the oval window anymore. The other one is sensory neural hearing loss, and that's when there's something wrong that goes inside the cochlea, where something happens where your cell hairs don't pick up vibrations anymore, or those information doesn't get transmitted into neural information. And this is the one that kind of people hear about when you hear, like, if you listen to your iPod for too loud for too long, that's really not damage to your conduction. It's not like your tympanic membrane like busts a hole in it. It's really that the inside the cochlea, your cell hairs become kind of used to this loud noise, and it reduces the sensitivity of the cell hairs. In that case, you can't hear as well anymore, and sometimes you could even go deaf. That's the bad news. The good news is that there's always cochlear implants. You could actually insert surgically a bionic kind of cochlea that could transmit that neural information back into the nerve. It's not as good, but it is doable. So it is replaceable. But still, turn down those iPods, friends. Turn them down.